In the first part of Chapter 19, we learned about what a magnet is. We're going to get more into what creates magnetic fields at the end of this section, but we also looked at what happened to a charge. And now we're going to start by looking at what happens to a charge when it's moving in a wire, both in a straight wire and a loop. So when we have a magnetic field, we now have three things going on. So in addition to our vectors of up and down, so we're going to say here the current is 0, but we could say the current is going up or down. We also need vectors into the page. So these vectors are going to go into the page representing an arrow, where if we're looking at the back of the vector, we're looking at an X, and if we're looking at the front of the vector, we're going to look at a point. So these blue X's indicate the magnetic field is directed into the page, or the tail of an arrow, where a dot would represent the head of an arrow. So these magnetic fields are going into the page. Using our right-hand rule then, you would point your fingers, representing your magnetic field, into the page. In this case, there is no current, there are no charges moving, so there's no force. Now when we look at the force on a wire, we're going to use our right-hand rule again, because a current is no more than a collection of charges moving. That's our definition of current. So our fingers will still represent the magnetic field, so we have lots of fingers. We said that the thumb represented the velocity. So when we're talking about a current carrying wire, that's going to be the direction of our current, it's going to be our thumb. And then our palm will be the force again. So here we have the force on that particular wire. We're going to look at these wires and what happens when we have a magnetic field applied to the wire when there's a current running through. Remember that the X's mean that the magnetic field is into the page. So that means we're going to stick our fingers into the page this way. So that's our hand. And then the direction of the current, so B goes this way. And then the direction of our current is up. I can draw that a little bit more up. Is more up. So our I is up. And then the palm of our hand would be to the left. So that means the wire will move to the left if the current is going up and the magnetic field is into the page. However, if the magnetic field is still into the page and we've switched the direction of our current, so now again we want to put our hand with our fingers facing in, but we want to flip it over. So this is my index finger and this is my pinky. Over here, this is my index finger and this is my pinky. So not the bestest hand, but now we want our thumb to point down. So basically you take your hand from the thumb pointing it up to just flip it over so your thumb is pointed down in the direction of the current, and then the force will be to the right. So you flip your hand over and your palm flips the direction, and so therefore the direction flips. So here's other versions of those drawings. So what's the equation for this? Well, we said that the force is equal to QVB times the sine of theta. That charge is moving, so we're going to write that velocity as length over time. And then we're going to move the time over from the length to the charge. This is the definition of current. So now the equation is BIL sine of theta. And that's the equation we use for current in a line, where L is the length of the wire, I is the current, and B is the magnetic field. So not surprisingly, we call this the Bill equation because it spells out BIL. Now it doesn't matter what order we put those variables in, but we might as well put them in a nice order to help us remember the equation. So now let's apply that equation. We know that the force is equal to the magnetic field times the current times the length of the wire. So here the figure has a magnetic field of this, just an order of magnitude less than the Earth's magnetic field. Then we have a 5 ohm resistor, that's R and V, and we want to find the magnetic force acting on the 2 meters of wire. So that's my length. Now we need the current. We found B, we have that, check. We have the length, check. We don't have the current, but we're given voltage and resistance. So we're going to use that in Ohm's law to find the current. The current is V over R, so we have 30 volts over 5 ohms gives us 6 amps. Now we can use our Bill equation to find the force is equal to 4 times 10 to the negative 5th Tesla times my current of 6 amps times 2 meters times the sine of 90 degrees, because these are perpendicular to each other. So they're 90 degrees. And so we get 4 times 10 to the negative 4th newtons. So not all that much force. Whether it actually moves will depend on how much resistance is in the system, like resistance to motion, like friction. But we don't know. So then they asked us, well, now your challenge question on the lesson would the force of the magnetic field change due to if we flip the direction? So if we flip the direction of the magnetic field from going into the page to going out of the page, does that change this number at all? So I'm going to take a minute to think about it. Okay, well, we do know that from the right-hand rule, if we basically have the magnetic field pointing in and current goes out of the battery from the positive terminal, because remember current is the flow of positive charges, so current is going up, we would point our thumb up, the force would be to the left. However, if we flip the magnetic field, instead of going in, coming out will come out, then that flips the direction of the magnetic field and the force would be the other way. That is the only thing that changes, is the direction of the force. So the number stays the same because we didn't change the angle. We just, well, went to the other direction. We went from plus 90 to negative 90. That doesn't change the value at all.